Have you ever wondered how an ultrasonic level transmitter works? It's a fascinating piece of technology that's integral to many industries. Here's the basic concept. The ultrasonic level transmitter is mounted at the top of a tank. It transmits an ultrasonic pulse down into the tank, which travels at the speed of sound. The pulse then bounces back from the liquid surface and returns to the transmitter. This is where the magic happens. The transmitter has an inbuilt microprocessor that measures the time delay between when the pulse was transmitted and when the echo signal was received. This time delay is crucial, as it helps the microprocessor calculate the distance to the liquid surface. In other words, the distance is calculated based on the speed of the pulse and how long it took to return. So essentially, the transmitter measures the time delay and uses this information to calculate the distance to the liquid surface. Now you might be wondering, how does the transmitter calculate the distance? Well, let's dive into the science behind it. The transmitter sends an ultrasonic pulse into the tank. This pulse travels at the speed of sound and is reflected back from the liquid surface. The transmitter then measures the time delay between the transmitted and received echo. The onboard microprocessor calculates the distance to the liquid surface using the formula: distance equals speed of sound in air times time delay, all divided by 2. Once the bottom reference, typically the bottom of the tank, is programmed into the transmitter, the liquid level is calculated by the microprocessor. It uses a simple equation: level equals tank height minus distance. The beauty of this technology is its precision. By calculating the time it takes for the ultrasonic pulse to return, the transmitter can accurately determine the level of liquid in the tank. This calculation allows the transmitter to accurately determine the level of liquid in the tank. There are several key elements to consider when it comes to ultrasonic level measurement. First, we have the minimum and maximum measuring distances, also known as the dead band and the maximum range, respectively. The dead band is a short range in front of the sensor in which the ultrasonic device cannot measure. On the other hand, the maximum range is the longest distance under ideal conditions that the device can measure. Now let's talk about the importance of time-lapse between firing the sound burst and receiving the return echo. This time-lapse is directly proportional to the distance between the transducer and the material in the vessel. In simple terms, the longer it takes for the echo to return, the further the distance. This principle is the core of ultrasonic measurement technology, and it's encapsulated in the formula: distance equals velocity of sound times time divided by 2. These elements are crucial in understanding the functionality of ultrasonic level transmitters. There are also practical considerations to keep in mind when using ultrasonic level transmitters. The frequency range for ultrasonic methods typically falls between 15 and 200 kHz. Lower frequency instruments are used for long distance and solid level measurements, while higher frequency devices are used for shorter liquid level measurements. The speed of sound, crucial in calculating distance, varies with the medium's temperature. To account for this, the transducer often contains a temperature sensor to compensate for changes in operating temperature. This ensures the speed of sound, and hence the distance calculation, remains accurate for level measurement. Another consideration is the presence of heavy foam or dust on the surface of the material. These can act as sound absorbers, affecting the performance of the ultrasonic device. Understanding these factors can help ensure accurate and efficient use of ultrasonic level transmitters.